All right, hey you guys, it's Mr. Frank. It's Sunday night. I hope you're doing well. I've been thinking about you a bunch, and I'm just so sorry that this is the way it is right now. Um, sure miss being in class with you. Um, so I guess so. The plan for this week is we'll cover chapter 13, achieving energy sustainability, and that'll send us into the break. I think for Wednesday's class, we'll do like an online vocab quiz. Open book, open note, talk with a friend. Everybody should get 100%. I'll put it up as a some kind of online format where you can log in and we'll do vocab for chapter 12 that way. So, and then there's also an article in Scientific American I'd like for you to read tonight. So we'll break this chapter into two parts. We'll do the first part today and the second part next time. I'll try to keep today to under 20 minutes. This is kind of an exciting chapter in that it's kind of showing where we can go with generating the energy that we need as humans on planet Earth, and show you that there's a way forward without fossil fuel usage. So, okay. Fill in the questions as we go. You can do the first half today and the second half on Wednesday. There's a Google Doc, just like last week, that I've shared with you up on the Power School site. And, this time there's fewer questions. I think it's 15 or 16 questions I have there. So, okay, so achieving energy sustainability. So, 46 terms. I think just about all of these are covered in the notes. A few maybe just from the reading. So please also read chapter 13 if you haven't already. Okay, what is renewable energy? Okay, so it can be rapidly regenerated, and some sources of renewable energy can never be depleted, no matter how much we use. So that's exciting. Non-renewable, remember, just a reminder from last week, non-renewable energy is things like natural gas, oil, coal, nuclear. Potentially renewable, things like wood, biofuel. This is production that's on human time scales. And then non-depletable, wind, solar, hydroelectric, geothermal. We've got lots of solar energy. We'll look at that coming in more than we could possibly ever use. And of course, the water cycle keeps going round and round, so we'll have water moving on planet Earth for the foreseeable future. And certainly there's lots of heat stored in the Earth itself. Okay, quick refresher. This is just looking at energy use by type over time, all the way up to 2014. So you can see, in 1700, everything really early on was biomass, just burning, wood or animal waste or, dried plant material. And then starting in the 1800s, you could see coal becomes, really important piece of the energy mix for humans. And then really, early 1900s, you start seeing oil take up a piece, natural gas. And then, again, in the 60s, 50s, 60s, 70s, you start seeing hydroelectric, nuclear, and, new renewable energies, still just a small piece of the total overall energy picture. Okay, how can we use less energy? That's an important piece of this. So Jimmy Carter was our president in the 1970s, and he encouraged Americans to get out there and conserve, use less. He was known as the sweater president because he told us, hey, maybe Americans, you want to conserve energy, and instead of heating your houses as much in the winter, maybe put on a sweater. And that is thought to be part of the reason he was a one-term president. So, but we can do that. We can lower our thermostat in the winter and have our houses be a little cooler. We're all seeing that we're driving fewer miles right now, and your homework last week showed that, we're not using our cars, we're using less energy, we have a cleaner environment. Okay. Also, the trend in energy efficiency, getting, more miles per gallon with more efficient vehicles, that kind of thing. All right, what can we do as individuals? Well, in our homes, we can do things like really, well insulate our homes really well, seal up any gaps so that the homes are sealed tightly from the environment and heat, and also air conditioning in the summer doesn't leak out into the environment. Make some changes with our thermostats. A lot of these Nest thermostats are helping increase efficiency. We can use less hot water, do laundry in cold water. We've definitely, as a campus, 90% of our light bulbs on campus are now LEDs. So, we can do that in our homes as well. Consider riding a bike, taking public transportation, carpooling, planning trips to maximize efficiency. Things like, appliances at home, buy Energy Star devices. These are things that are rated for efficiency in terms of using electric current or using less electric current. Unplug power, appliances when possible. Use a power strip. We've all kind of switched over to laptops. That's also been a big energy saver. Okay, just kind of moving quickly through this. Again, pause if I'm going too fast, but conservation and efficiency. So energy companies have looked at their, their basically use during peak demand periods, and realize that they're supplying lots and lots of electricity during certain hours of the day. Most of us have similar behaviors in terms of, starting the dishwasher or doing the laundry or turning on our air conditioners. So this idea of peak demand, the time of day when the greatest amount of energy is used. Utilities have figured out this variable price structure, and they're incentivizing customers to use energy at off-peak hours, and you can actually pay less during those off-peak hours. So what does that look like? Okay, here's the green line here. It looks like a mountain. Shows kind of the peak period of energy use between 1 p.m. and 7 p.m. every day. That's when the most greatest number of people are turning on appliances and using different electrical, drawing load from the grid. Okay, so getting folks to think about shifting their energy use to this off-peak period. And if we look here, here's peak day pricing, summer pricing. So you can see that if you're using power during the peak, you're paying 85 cents. This is per kilowatt hour. And if you shift your energy use, to those off-peak times, between 12 a.m. and 8:30 a.m. by maybe putting appliances on a timer, you can drop that 85 cents an hour down to, or 85 cents a kilowatt hour down to about 20 cents a kilowatt hour. So incentivizing savings for customers by using electricity different times of the day. Okay, what's sustainable design? This is looking at buildings. We have the AEC on campus. It's LEED Gold certified. The company that helped us build the AEC had people that had majored in sustainable design, improving the efficiency of the buildings that we live in and that we work in. Okay, things like looking at the materials that the buildings are made out of, designing an electric system for the buildings that's really efficient. Really efficient air conditioning, incorporating water efficiency strategies. Okay, a home. People, when they're building and buying homes, they can do things to increase the efficiency. Putting a shade tree in the southwest corner of the house can dramatically reduce the need for cooling. Putting eaves on the front porch to shade the interior of the house during the summer months can also increase efficiency and lower energy use. Double pane windows, really strong insulation, high efficiency heating and cooling system. All these things can save both money for the homeowner and energy in the long run. Lots of sustainable design folks are looking at passive solar energy. The idea of the sun taking, relative to us, a higher track in the sky during the summer months and appearing the apparent position of the sun in the winter being lower in the northern hemisphere in the sky. And it's really because of our angle, the fact that we're tilted on our axis during those summer and winter months. So it's not actually the sun shifting position, but rather us in our travel around the sun. But taking advantage of that, many new buildings that are sustainable design or have incorporate elements of sustainable design do things like create these eaves where the summer sun is not shining directly into the house, rather it's shaded. Again, it's higher in the sky, apparently higher in the sky, and the winter sun is tracing a lower angle, again because of our position. And that winter sun can actually shine directly through the windows and heat maybe a thermal mass, like a large concrete slab on the underside of the house. And this is passive solar energy, basically incorporating extra heating from the sun in the winter and reducing the amount of solar exposure in the summer by using those eaves, those extended roof lines. There's another example of that, just so you can look at that. Winter, we get a heat absorbing floor, the sun shining in through the window, and heat is collecting in that floor and it can re-radiate out into the interior space. Whereas in the summer, when it's hotter, you've got the sun being blocked by part of the overhang of the roof. Okay, here's some sustainable designs, different buildings taking advantage of these kinds of things. California Academy of Sciences in San Francisco, and the AEC. We're LEED Gold certified, and many of those concepts are incorporated into that building. Okay, we're gonna wrap it here in just a minute. We'll just preview the rest of the chapter here and maybe just dive in just a little bit. We're going to look at all the different forms of renewable energy. But this is just showing spheres that are relative in size to each other in terms of the total ability to provide energy for humans on Earth. And what's the biggest piece here? The sun. So, this is all of these things are in something called terawatt years. It's just a measure of energy, like a BTU kind of. It's not equivalent, but by any stretch. But the idea of it's just a unit of measuring energy. And you can see that the sun is providing 23,000 terawatt years per year. It's far bigger than any of these other pieces. And you can compare there. And so what that's saying is that there's a tremendous amount of potential for solar energy to be embraced by humans moving forward. Okay, the rest of the chapter is a survey of renewable energy types. I don't think I've gone too long here, so maybe we'll just do one or two and then we'll do the rest next time. So, we know that biomass is plant material that's energy, really indirect energy from the sun. It's, photosynthesis harnessed and turned into, long chains of sugars, sugars chained together to form starches that we can then, use for any number of things. So, biomass is widely used by people in developing countries all around the planet. So, ultimately the sun is the source of everything, that we have. We've got fossil fuels, which are, the ancient stored sunlight, fossil sunlight, if you will. It's ancient plants and algae that were compressed in the geologic strata of the earth and stored over tens, if not hundreds of millions of years for us to come along and begin to extract. And then you have renewable energy, from the sun, directly solar energy. Of course, differential heating of the earth by the sun creates wind, drives the water cycle. So you've got wind and hydroelectric power. You've got solar heating of the ground. So you can do ground source heat pumps through that. And then you've got biomass there, wood, charcoal, other plants, possibly algae. We'll look at that for homework tonight. Manure. Many people in developing countries burn cow manure and different types of manure for both cooking and heating. And we've got liquid biofuels under production. And then within the crust of the Earth itself, you have non-solar related energy, things like nuclear fuels, uranium, also gravitational pull of the moon in relation to the sun, creating tidal energy that can be harnessed. Okay, so biomass again, wood, charcoal, manure, ethanol, biodiesel. These are biofuels that are created from plant material. And lots of biomass resources in the U.S. Lots of places where there's biomass that's being utilized, and ethanol, for example, being produced in the Corn Belt. Here's clearing a forest to create charcoal, which is still used by hundreds of millions of people for cooking. Okay, let's wrap it with this. So modern carbon versus fossil carbon. So, the idea of burning biomass, it's modern carbon. It's wood that's produced on an annual basis or, on a human time scale. So that's modern carbon. Anything that's that we've discussed that's like biomass, that would be considered something that's being created on a human time scale again. But coal is fossil carbon that's been stored in the crust of the earth again for millions of years. Oil, natural gas, these are fossil carbon. And this is carbon that, again, has been stored there. And when we combust it, the byproducts of that are carbon dioxide that get up into the atmosphere. And we're going to look at climate change as kind of our last thing. Okay, so modern carbon, tied to biomass, tied to annual production through photosynthesis, and fossil carbon, coal, oil, and natural gas, carbon that's been stored in the crust for millions of years. Okay, so that's enough for today. Take a look at the homework on the calendar. There's an article I'd like you to read and answer a couple questions on. And just please drop in on the office hours if you have any questions. I'm thinking of you guys. Okay. Take care.